My name is Ravanthi, lecturer in Mathematics, Gov Degree College for Women, Karimnagar. Today's topic, cosets. Definition: if H is a subgroup of G, then the set AH equal to AH, H belongs to H, is called the left coset of H in G generated by A, and the set HA equal to HA, H belongs to H, is called right coset of H in G. We have two cosets, left coset and right coset. AH small element is left coset, then it is called left coset. AH is called left coset, HA is called right coset. Properties of cosets. First property, if H is any subgroup of a group G and A comma B belongs to G, then A belongs to AH. Here H is any subgroup of group G and A comma B belongs to G, then A belongs to AH. Let we prove this condition. Let E be the identity in G, that is E belongs to G. H is a subgroup of G. Subgroup means it is also a group, so E belongs to H also. E belongs to H since H is a subgroup of G. Here we have E belongs to H, implies A equal to AE belongs to AH, implies A belongs to AH. Here we have this condition. Since G is a group, so by identity, and H is also a subgroup, so A into E equal to A. A into E means belongs to AH. Second property, we prove AH equal to H if find only if A belongs to H. Here we prove two conditions. AH equal to H if and only if A belongs to H. If condition, let AH equal to H implies A belongs to AH implies A belongs to H. Here we have the condition AH equal to H, so A belongs to AH from one condition. Since one condition, here we have AH equal to H means A belongs to H, therefore AH equal to H implies A belongs to H if condition is true. Only if condition let A belongs to H implies AH belongs to A into capital H for small h belongs to capital H. A belongs to H comma small h belongs to H implies A into H belongs to H, since closure property. Here AH belongs to AH, here we have AH belongs to H implies AH is subset are equal to H. Since A belongs to H implies A belongs to AH implies H subset are equal to AH. From these two conditions, AH is subset are equal to H and H is subset are equal to AH, therefore AH equal to H. Only if condition is true. Therefore AH equal to H if and only if A belongs to H. Second condition we prove. Third one, AH equal to BH if and only if A belongs to BH. In if condition, let AH equal to BH since A belongs to AH implies A belongs to BH. Therefore, AH equal to BH implies A belongs to BH since AH equal to BH. This condition we have. If condition is true. Only if condition let A belongs to BH implies multiplying both sides by B inverse A belongs to B inverse into B belongs to BH. Here B inverse A belongs to H since by inverse property B inverse into B equal to E. With respect to multiplication 1, so we write 1 also. Here we have the condition B inverse A belongs to H. Next we write B inverse AH equal to H. Since AH equal to H implies A belongs to H. We use this condition. Next, both sides multiplying with B into B inverse AH equal to BH. Again from inverse property we write E into AH equal to BH, since by inverse property. Again we use by identity property. E into AH equal to AH implies AH equal to BH. Therefore, AH equal to BH for A belongs to BH only if condition is true. Hence, AH equal to BH if and only if A belongs to BH. Third property is also proved. Next property, AH equal to BH or AH intersection BH equal to pi implies any two left or right cosets of a subgroup are either identical, disjoint or identical. Here we prove this condition. AH equal BH or AH intersection BH equal to pi implies any two left or right cosets of a subgroup are either disjoint or identical. The two left cosets, here we take left cosets, we take any cosets of a subgroup H are AH and BH. We suppose that two left cosets are AH and BH if they are disjoint, then AH intersection BH equal to pi. Let AH intersection BH equal to pi not equal to pi, then there exists at least one element C such that C belongs to AH intersection BH implies C belongs to AH and C belongs to BH. Here we suppose that C belongs to AH intersection BH. So C belongs to AH and C belongs to BH implies C equal AH1 and C equal BH2 for H1 comma H2 belongs to H. Here C both are equal to C, therefore AH1 equal to BH2. Multiplying both sides by H2 inverse, AH1 into H1 inverse equal B into H2 into H1 inverse. Implies A equal to B into H2 into H1 inverse. A equal to BH3. Since H3 equal to H2 into H1 inverse belongs to H. Here A belongs to BH. Also A belongs to AH implies AH subset are equal to BH. Similarly, we have BH subset are equal to AH implies AH equal to BH. Here H3 belongs to H, so A belongs to BH. Also A belongs to AH also. Therefore, AH subset are equal to BH. Similarly, we have the condition BH subset are equal to AH. From these two conditions, AH equal to BH. Therefore, the two left cosets are either disjoint or either equal or disjoint. Next property, AH equal to BH if and only if A inverse B belongs to H. Let AH equal to BH implies B equal to BE. From identity now, BE means belongs to BH. Therefore, we have the condition B belongs to BH. Here we have AH equal to BH, so B belongs to AH. Since AH equal to BH, implies multiplying both sides by A inverse B belongs to A inverse AH. Here we have A inverse B belongs to H, since by inverse law A inverse into A equal to E. Here we have A inverse B belongs to H. Therefore, AH equal to BH implies A inverse B belongs to H. First condition is true. Next, we suppose that let A inverse B belongs to H, multiplying both sides with H, A inverse B H equal to H. Since AH equal to H implies A belongs to BH. We use this condition and multiplying both sides with A into A inverse BH equal to AH, and again by inverse law we write A into A inverse equal to E, A into BH equal to AH. Since by inverse law. Next, by identity property, we write A into BH equal to BH. Therefore, BH equal to AH implies AH equal to BH implies A inverse B belongs to H. Next property, To prove that order of AH equal to order of BH, here we take the mapping F AH to BH, where F of AH equal to BH for A comma B belongs to G. Let AH1 equal to AH2 for all H1 comma H2 belongs to H. Here we take H1 equal to H2 implies BH1 equal to BH2. Both sides we take the function f of BH1 equal to, okay, here we take AH1 multiplying with f of AH1 equal to f of AH2. F is well defined, the function is well defined. F of AH1 equal to f of AH2 for all H1 comma H2 belongs to H. Here we take the condition f of AH1 equal to, we have BH1 equal to BH2. Since f of AH1 equal to BH1 comma f of AH2 equal to BH2, here BH1 equal to BH2 by left cancellation law. Since by left cancellation law B is cancelled, we get H1 equal to H2, and multiplying with both sides AH1 equal to AH2. F is 1 1. Also B H dash belongs to BH implies H dash belongs to H, implies AH dash belongs to AH, multiplying with A. Here BH dash equal to F of A into H dash. F is onto, implies the function F is mapping from AH to BH is 1 1 and onto. Therefore order of AH equal to order of BH. Next property, AH is a subgroup of G if and only if A belongs to H. Let AH be the subgroup of G implies E belongs to AH, also E belongs to EH, since E belongs to G. AH intersection EH is not equal to pi, non-empty set, implies AH equal to EH equal to H. Since AH equal to H implies A belongs to H. AH equal to H. A belongs to H. implies AH equal to H. Here in this property we prove that A belongs to H. Next property, let A1H comma A2H so on AKH be the different left cosets of H in G. A belongs to G. Next property, let A1H comma A2H so on AKH be the different left cosets of H in G. A belongs to G implies AH equal to AIH, where 1 is less than or equal, I is less than or equal to K, implies A belongs to AH. Each A belongs to G must belong to AIHI belongs to AIHI for 1 is less than or equal, I is less than or equal to K. Therefore, A1H union A2H union so on union AKH equal to G. Next we solve problem. If H equal to 0 plus or minus 3 plus or minus 6 plus or minus 9, find all the left cosets of H in Z. Here given H equal to 0 plus or minus 3 plus or minus 6 plus or minus 9. Find all left cosets of H in Z. Solution. Given H equal to 0 plus or minus 3 plus or minus 6 plus or minus 9. Z equal to, we take integer set 0 plus or minus 1 plus or minus 2 plus or minus 3 so on. The left cosets of H in Z is given by A plus H, where A belongs to Z. 0 plus H equal to 0 plus or minus 3 plus or minus 6 plus or minus 9 so on equal to H. 1 plus H equal to 0 plus or minus plus 1, 1 plus or minus 3, 1 plus or minus 6, 1 plus or minus 9 so on. Here 0 plus 1, 1, we take plus 4 and minus 3, 1 minus 3 minus 2, 1 plus 6 7 and 1 minus 6 minus 5, 1 plus 9 10, 1 minus 9 minus 8 so on. This is 1 plus H equal to minus 8 minus 5 minus 2 1 4 7 so on. 2 plus H equal to 2 plus 0 2 plus or minus 3, 2 plus or minus 6, 2 plus or minus 9. 2 plus 0, 2, 2 plus 3, 5, 2 minus 3, minus 1, 2 plus 6, 8, 2 minus 6, minus 4, 2 plus 9, 11, 2 minus 9, minus 7, so on. 2 plus h equal to 2, 5, minus 1, 8, minus 4, 11, minus 7, so on, equal to minus 1. The set is equal to minus 1 plus h. Minus 1 plus h equal to minus 1 plus 0, minus 1 plus or minus 3, minus 1 plus or minus 6, minus 1 plus or minus 9, so on, equal to minus 1, 2, minus 4, 5, minus 7, 8. Here minus 1 plus 3 plus 2, minus 1 minus 3 minus 4, minus 1 minus 6 minus 7, minus 1 plus 6, 5, minus 1 plus 9, 8, and minus 1 minus 9, minus 10 also, so on. Minus 1 plus h equal to minus 7, minus 4, minus 1, 2, 5, 8. Minus 2 plus h equal to minus 2 plus 0, minus 2 plus or minus 3, minus 2 plus or minus 6, minus 2 plus or minus 9. Minus 2, 1, minus 5, 4, minus 8, 7, minus 11. Minus 2 plus h equal to minus 11, minus 8, minus 5, minus 2, 1, 4, 7. This is equal to 1 plus h. Plus 3 plus h equal to 3 plus 0, 3 plus or minus 3, 3 plus or minus 6, 3 plus or minus 9, equal to 3, 6, 0, 9, minus 3, 12, minus 6. Minus 6, minus 3, 0, 3, 6, 9, 12. Here we get 0 plus or minus 3 plus or minus 6 plus or minus 9. 3 plus h is equal to h. Similarly, minus 3 plus h equal to h, 4 plus h equal to 1 plus h, and minus 4 plus h equal to minus 1 plus h, and so on. Therefore, all the left cosets of h in z are h comma 1 plus h comma minus 1 plus h. Next theorem, Lagrange's theorem, very important theorem. Lagrange's theorem. Statement: if G is a finite group and H is a subgroup of G, then order of H divides order of G. Statement is G is a finite group and H is a subgroup of G. Then order of H divides order of G. Proof. Let G be a finite group and H be a subgroup of G. Let the order of G and H be M and N respectively. Implies order of G equal to N, order of H equal to M. Here we suppose that order of H and G be M and N respectively. If A1H, A2H, so on, AKH are distinct left cosets of H in G, then A1H union A2H union so on AKH equal to G. Applying modulus on both sides. Modulo of A1H union A2H union so on AK union AKH equal to order of G. Here A1H A2H mod of A1H plus mod of A2H plus so on mod of AKH equal to order of G. From the properties of cosets, order of AH equal to order of H equal to M. Substituting the corresponding values in the equation M plus so on M K times equal to N. M can be written as K times, so M into K equal to N implies K equal to N by M. It can be seen from equation that M divides N. Therefore, order of H divides order of G. Hence, proved. Lagrange's theorem. This is called Lagrange's theorem. If G is a finite group and H is a subgroup of G, then order of H divides order of G. Here in this proof, let G be a finite group and H be a subgroup of G, and we suppose order of G and H be M and N respectively, order of G equal to N and order of H equal to M, and we take distinct left cosets of H in G, A1H union A2H so on AKH equal to G. Next theorem. every group of prime order is cyclic. Every group of prime order is cyclic. Here we use Lagrange's theorem. Let G be a group and prime number P is the order of the group. That is order of G equal to P. Since P is greater than 1, thus there is an element A belongs to G such that A is not equal to E. The cyclic subgroup generator A generated by A is a subgroup of G and it has at least two elements A and E according to Lagrange's theorem. The order of generator A, that is order of generator A divides P. Let generator A equal to Q, but P is a prime number. Therefore, Q equal to 1 or Q equal to P. Since A is not equal to E, implies order of generator A is greater than 1. Order of generator A is greater than P. Generator A equal to G. G is called cyclic. Therefore, every group of prime order is cyclic. Every group of prime order is cyclic. Here we use Lagrange's theorem. In this proof, let G be a group and we take the prime number P. Order of G equal to P. Since P is greater than 1, there is an element A belongs to G such that A is not equal to E. Here, according to Lagrange's theorem, order of generator A divides prime P. Let generator A equal to Q, but P is a prime number, Q equal to 1 or Q equal to P. Since A is not equal to E, order of generator A is greater than 1. Order of generator A is greater than P. Here, generator A equal to G, G equal to P. So, G is called cyclic. Every group of prime order is cyclic. Hence, proved. Today we are discussing cosets. We have two cosets, left coset and right coset, and the properties of cosets, Lagrange's theorem, and another theorem is every group of prime order is cyclic. Thank you.